a lot. It's really a great pleasure to be here. I would like to thank the organizer, the program committee. Is a fantastic location, and to be on this stage is really a great honor. So during my talk, my short talk, I would like to present you really some very, very latest news from our lab. And indeed, I would like to give you two news, and the first one is related to the title I originally gave, and that's our study of the Roton spectrum, and this very special collective excitation that you can have in dipolar quantum gas. And the second part, which are just few slides, it's kind of an update from our new experiment. And indeed, we decided to combine together two highly magnetic atoms, so erbium on one side and dysprosium on the other. And we actually now achieved to produce the first heteronuclear dipolar quantum mixture by combining both of them. So I will now start with the first part. So I think that in the community of people working with long-range interaction in many different settings, as we heard today, it was really very fascinating here with many new phenomena. In the subgroup of people working with magnetic atoms, actually, I think that the last couple of years showed really the power of this system to investigate not only very advanced platform in quantum physics, but also very fundamental problem related to the notion itself of quantum fluid, of superfluidity, and merging our quantum gas to other field. And so from the first pioneer seminal experiment done in Stuttgart back in 2008, where actually they observed in chromium this patterned collapse, which is now known as D-wave collapse. Many things happen after this fantastic work. More recently, the group of Stuttgart actually observed that there is a new type of phenomena which play an extremely important role and give rise to the formation of a stable crystal of droplet. Let's say it's kind of a new phase in our system. We joined the investigation of Stuttgart and showed also in Erbium that you can either have many droplets, but also you can create macro droplets. So a single droplet in which the notion of the high density Bose-Einstein condensate become a little bit obsolete, because you can actually create a even denser state, which is this macro droplet, and this one will be stabilized by quantum fluctuation. And very beautiful experiment by Tillman and his group with dysprosium also show this type of microdroplet and, let's say, self-bound properties. And so from these, of course, there were other experiments going on just in the last couple of years, in which actually you can use long-range interaction in lattice type of system and studying long-range correlation. Or you can even show, like we have done with the fermionic erbium, that even identical fermions actually can interact, and these have impact on the few body physics and the many body physics. So among all these experiments, I have to say that few of them, and in particular the droplet physics, was highly unexpected. So it's really a beautiful example of how counterintuitive dipolar interaction can be, and also a beautiful experiment, a beautiful example about the fact that you can have observation going, let's say, before prediction. However, in the field of quantum gases with magnetic atom, there have been a prediction that for many years, let's say, remain unobserved. And this is a prediction done back in 2003 by Luis Santos, Goran Shlapnikov, and Levenstein, showing that actually the way a system would respond collectively to excitation can be extremely different in presence of dipole-dipole interaction. And so this was the prediction in 2013, so about 15 years ago, about the fact that the spectrum of collective excitation in quantum gas can be extremely modified from the case of a non-dipolar gas and can show a very special minimum at large momentum. So this actually is a pretty amazing properties, and this original work have motivated a lot of investigation, and also maybe it's the reason for some of the quantum gas experiment to be started. And I have to mention that my talk will only focus on magnetic atom, but there is also other proposal in 2003 by Odell and co-worker working on infinite range interaction in light-induced dipole, and very beautiful experiment of the realization of this idea in BEC in cavity from the group of Tillman-Esslinger, and also other Roton-related experiment. But I will focus only on the magnetic dipolar case. So it's a dipole-dipole interaction. And so here, it's very amazing because what do you see? You see that actually with a very low cost of energy, you can introduce into the system high momentum excitation, and the system will collectively respond to this type of excitation. And this is also impressive because it makes another similarity which we thought it was beyond reach, and I will tell you why, because it makes a very strong analogy with the so-called Roton spectrum, let's say, predicted back in 47 by Landau and then observed 50 years ago in neutron scattering experiment using helium superfluid. So that's the spectrum, and so you have a phonon part that's already a collective excitation. You see the energy is linear, there is sound velocity, but is a macroscopic excitation, a collective excitation of the whole system, and then you have this maxon and then this Roton minimum. In helium, the existence itself of the minimum as a reason that the interaction between helium atom is extremely, extremely strong. So, and at that time, there was a lot of study in the early time to try to understand what is the meaning of this new quasi-particle, the Roton. And it was thought it was really, let's say, like ghost of local vorticity, but actually it's not. This minimum that appear and eventually soften, it's kind of giving you an instability of the system toward crystallization. So the system in helium, they try, let's say, to make local order at short wavelengths. And in Nozière, in one of his very nice paper, he wrote, okay, that's something, the Roton minimum is something special to helium. Indeed, in a weakly interacting dilute gas, there is no Roton minimum in that case because the interaction were too weak, the correlation too weak. And indeed, the experiment with weakly interacting Bose-Einstein condensate of non-dipolar atom back in 2002, they showed that the spectrum of excitation do have this phonon mode, this long wavelengths mode, which is this acoustic wave, and then it's free particle, but there is no such a Roton minimum in the spectrum. And then for weakly dipolar BC, also the Roton minimum have not been observed because the dipole-dipole interaction was not strong enough, but you still already see in the spectrum of excitation, of the collective excitation, a fingerprint of dipole-dipole interaction because depending on the orientation, so the sound velocity of the phonon part is a little bit different, showing an isotropy in the sound velocity. And so now, if you move to even stronger atom, then you actually do expect really to see a Roton minimum. And if you now think that our gas not only have dipole-dipole interaction, which is long range and anisotropic, but also have contact interaction. The contact interaction can be used as a tool to completely soften the spectrum until, I mean, you get zero energy, so it costs no energy to create this excitation, so the system becomes unstable, and eventually the Roton gap becomes imaginary, and you can have this exponential population of this mode. So there have been a lot of intense theoretical work over the many years. I'm sorry if I'm not listing someone. And I mean, exploring many different features, which all of them, each of them are very fascinating. I don't have the time. Of course, one important point was to extend the calculation originally done to an infinite homogeneous system to the case which actually we do have in the lab, so a finite size system with a trap in which the density of your gas is not the nice box like Zoran, but you have actually a density that change in space. And here, I mean, it was the concept also from the group of Luis Santos of this Roton confinement. It's very nice. So there is, this Fourier conjugate approach. So if you have an excitation at some momentum, then in space you will also have an excitation. In our case, we have an excitation of the Roton at large momentum. That means that the system will create very small wavelength density modulation. But it's also amazing to see that over this 15 years, almost all the theory was always considering axial symmetry. Let's say a sort of a various version of a 2D pancake, because it's easier to probably also calculate but you will see that this will play an important role. And now let me come to the experiment, which is a joint work between the group of Luis Santos, my group in Innsbruck, and also Rick van Biesen, which is now postdoc in the Peter Zoller group. And so let me summarize the key idea once more and the key ingredient. So the main idea is that we want to access the spectrum of excitation. We want to see whether the Roton exists or not. And then if I make the Roton spectrum completely soft, so that it touched zero, then I start to enter in the Roton instability. What does it mean? It means that what it can happen for zero or imaginary gap is that the mode itself gets populated. So a K0 momentum atom can actually create a pair of K plus minus K rot, okay? And so, and this was the idea, so to then change the scattering length pretty fast and try to see this instability, and so the emergence of Roton population from our experiment. To do this is not so easy because the softening is very fast in scattering lengths. So you need to know your scattering lengths extremely well and extremely precise, and this took us a lot of work. But here is the first ingredient is the tuning of the scattering lengths, and here you see our spectroscopy mapping, which we have done in dedicated lattice experiment. And this is kind of tuning of scattering lengths to soften was the first ingredient. The second ingredient is the probing, because as I told you, so high momentum excitation correspond to small wavelengths modulation of the density in trap. And so that means that if the Roton mode gets excited, in trap you will have this type of modulation, and when you do the usual time of flight experiment, you will map the density modulation. You will see this, the appearance of these two modes. So for us, the probing was simply time of flight imaging, let's say. And then the third ingredient, which actually was very crucial, also if we didn't expect to be crucial, is that, as I told you, all the experiments have studied the kind of axial symmetric trap. That means if you have to create plus minus k, every plus minus k, they are degenerate in this circle, okay? And so that means that the intensity for each pair of k, it's not very high. But now if you put it in a tube, like we did, so what you get is that the focusing, because now there are only the linear momentum plus and minus, which satisfy the relation. And so let's come to the experiment. So here we have our spectrum. We started with a normal Bose-Einstein condensate, inverted aspect ratio in time of flight as expected, and we decreased the scattering length, and then you see the appearance of this Roton excitation. So, and then you can even soften and get more population. So from the Bogolyubov theory, I mean, you expect that the rate of growth of the Roton population can be directly connected to the Roton gap, so the energy. And so here we studied, I mean, you have this exponential growth in our experiment, and then you see that you have a saturation because at longer time we start to lose some atom, and so it gets saturated. But the most important part is this exponential growth, and from this we can directly measure the imaginary Roton gap. And so here, it's the different growing of the Roton mode in our time of flight experiment for different scattering lengths. And now there is a unique relation in scattering length and time that allows us to, let's say, rescale the time. And if we rescale, all the curves, similar to what Misha just told us, are now collapsing one on top of the other. And so we see a universal scaling. And from this and this type of treatment, we can directly, from the growth of the Roton peak, which is exponential as a function of the imaginary gap, from this time, we can directly measure the imaginary gap in our experiment. This was for us very nice. On the other hand, I mean, I want to point you that the Roton spectrum, I need to find my, so now the time, so I'm changing the scattering length and look from calculation done by Rick, how the spectrum is actually changing. And you will see that at the end, I have to slow down the video because it's very sensitive to the scattering length. And if I manage, yes. And this is the Roton softening. And now see, by changing very little the scattering length, you can completely, let's say, Rotonize the spectrum. And here the spectrum will be imaginary. But we wanted also to probe the real part of the spectrum. So we want to probe the spectrum of excitation when the gap is not completely Rotonized. So to have a stable gas, stable ground state, no instability, and on top of this, the excitation have this minimum. And so to do this, I mean, there is a way to probe the spectrum of excitation with very beautiful experiment done in the years, which is Bragg spectroscopy. So in our experiment, Bragg spectroscopy was a little bit of a challenge. First of all, we wanted to see up to very high momentum, so we needed to change the momentum a lot, and that's not easy. Everybody that have done Bragg spectroscopy, I think, knows that it's not always so easy. And then the concept is that you have to transfer momentum, and that you do this by sending two beams. And now if you change the angle between the two beams, you can change the momentum. And this is, you can do nicely with new device, for example, the digital mirror device. That's how we did. In our experiment, we had the problem. We had absolutely no optically access. So we thought it was impossible to do this, but I have to say we had a special so the team had really a special ingredient, and the special ingredient is our PhD student in kind of Superman attitude here, because he was so motivated and he thought to be able to make space and to have the Roton. And actually he also convinced Swarovski to cut a lens with the right shape for us and for free. I don't know, so this guy is scaring me. And also then another Gabriele joined the experiment, and together at this very nice experiment. And so now let me just go to the final result. So this is the spectrum of excitation measured when the scattering length is high enough to not have the Roton minimum. And this is how we decrease the scattering length and how things start to become flat, and then really Rotonize with the nice maxon and Roton minimum, and the phononic dispersion. So there are a lot of work. This is really preliminary things. There is a lot of work that we have to do, and also the agreement between theory and experiment is getting worse while we Rotonize, and maybe this points us to some weakness in our approach, or really that the quantum fluctuation which are in the model has to be taken account in a different way. We can discuss later about this, because I have just 3 minutes left, and yeah. And so all these experiments about the Roton have been done by our Erbium team, and here Gabriele and Dani are here at ICAP. They will be happy to tell you more. In the last really 2 minutes, let me point out that we have now a new experiment in Innsbruck, which is a little bit special for me, because I mean, you have 13 atomic species both condensed, I mean, in the periodic table. And for sure, rare earth atoms like erbium and dysprosium are the one which have a most complex atomic spectrum, anisotropy, F-shell, and multi-electron atom, many transitions. So it's very complex, and maybe it's scary, but actually each of them, we find out together with other teams around the world that they're pretty easy to cool down. And so they really, the approach to quantum degeneracy is actually very easy. And for us, the next step was to then combine two of them to create the first dipolar quantum mixture, in which the interspecies interaction will not be only contact as this mixture that we know, but will also be dipole-dipole. Now, this is the team, and Claudia, she has a poster on Thursday, and she can tell you more. And let me point to the richness. So you have erbium and dysprosium, both of them magnetic, different magnetic moment. You can study dipolar imbalance. You have a lot of bosonic and fermionic isotope. You can create Fermi-Fermi, Bose-Fermi, Bose-Bose mixture, and you can create this in multiple combinations. And actually, the matrix, just accounting the isotope, which are very abundant, are 16 possible isotope combinations. So very recently, we published our first double Mott experiment in which we show that we can actually cool very easily. And then in lanthanide, once you have the Mott, everything it's very easy. And so we produce the single species BC, so not mixture, just a single of them of all the isotope in this experiment. And then very recently, and actually there is an archive from last Friday, we have now double Bose-Einstein condensation of erbium and dysprosium simultaneously. And not only this, so this is the matrix of possible combination. We studied many of them, all the Bose-Bose and one Bose-Fermi. And so here you see the different combination of mixture that we can do, including with the Bose-Fermi with T over Tf. And now you can notice something, that now this is the thermal cloud, and the BEC is displaced at the center with respect to the thermal cloud. Now the fine observer will down see that actually dysprosium is pushed up and erbium is pushed down. And if this is in the mixed experiment, if you do single species, they are completely centered. So we see indeed already an effect of a repulsion, many-body repulsion, which now is contact and dipolar. But we have no idea about the scattering lengths. And if we now remove dysprosium, suddenly we can see how this cloud oscillates to find the new equilibrium. And the same in a similar experiment if we remove erbium and study. And with this, I mean, it's just a preliminary study. I think we can use this method of oscillation to get the global interaction of the system in collaboration with Michele Modugno. And with this, I would like to thank everybody for the attention and, of course, the team.